physics, electricity. And we begin.
So,
Yeah.
about the essay,
Oh yeah, what about it?
you giving back the feedback?
Oh, I gave feedback. Oh yeah, you submitted later, didn't you? Yeah, I gave feedback to people last week, but you said you were going to submit on Monday. Yeah, yesterday. Okay, thanks for reminding me. When I get back to the office after lunch, I'll look at your one. Did you submit last week a draft? Yeah, so I gave you a little bit of feedback, didn't I? Everybody's is actually okay. I just feel like people need to recheck the checklist.
So,
Yours, I gave you feedback on your draft. Did you see it? On Moodle?
On Moodle?
Yeah, feedback. You have to look, yeah. It's very important you read it because there's a problem with your introduction and conclusion. You want to check that, okay?
Okay.
Yeah.
if I have only 2 failures, is it okay or preferably 3?
Diagrams?
Yeah.
That's fine, yeah, that's fine. Yeah. I'll try to remember to check yours after lunch. You uploaded it to the draft link on Moodle. That's good, okay. Right, charge and current. We can get started with this. Yeah, got that? So, let's have a look. Right, so you know from chemistry, this is not new, you know from chemistry, or even middle school, that you have this thing called electric charge. And it's a basic feature of electrons, protons, and other particles. So, electrons are negatively charged, we say, and what do we say protons are? Positively charged. And neutrons? Neutral. Yeah? So, this is not new, right? You know this from chemistry for weeks and weeks now. Things that are negatively charged and things that are positively charged, what happens between them? They attract, don't they? Yeah. And if they're both positive or they're both negative, what happens? Repel, yeah. So the positive and negative is what helps the electron stick to the proton because they're attracted. Yeah. You probably talked about this in chemistry. So things that have the same charge push each other away. So 2 electrons separate, or 2 protons want to separate. Okay. What would you call this? What do you call this in chemistry? This law or this observation? Do you give it a name? No? No name for it? If you were to give it a name, what would you call it? Come on, make up a name. Use your English.
Law of attraction.
I like it, yeah. This could be perhaps that, yeah. Maybe law of charges. Maybe law of like and unlike charges. Something like this. So it's called the law of charges. But what you said, it could have been that as well. But I suppose the only problem with your one is that it doesn't include the repulsion one. So this is the law of charges. Now you don't need to write this down because I feel like you all know this very well from chemistry. Okay. So what's called the law of charges. Like repels, unlike attracts. Yeah? You know this from chemistry? Yeah. So on to something now more with physics. So we have this thing called an electric current, and that's actually just a flow of electric charge. So imagine you have some electrons and they're moving along. We call that a current. Or if you have some protons and they're moving along, we call that a current. Okay? These are just electric currents. They're just moving charge. In fact, you also know about this in chemistry, because you probably have learned that in a metal you have free electrons. You know, in a metal the electrons are free, so they can move around in the metal. This is what makes it a conductor. I hope I'm telling you stuff that you know from chemistry, yeah? But I don't know, has Lorraine talked to you about current? Is this a word that has come up in chemistry? No. Would you just say like a flow of electrons or a movement of electrons? Yeah? So that's all a current is. It's just a movement of charge. So I need you to write this down. An electric current is a flow of electric charge. Yeah? Got that? Yeah. So in a metal, it's free electrons that flow. And here's a little picture of it. So, I mean, this is, something like maybe like a copper wire, and the electrons move in the copper wire. It's not very complicated. I think I would like you to draw this as an example. It'll help you remember current. So just call this picture current and just draw this here. Just a little picture here, it'd be helpful. Siba, did Kim say she'll be late or what's happening?
She texted me during math and she said she'll come in 10 seconds.
Alright.
I think she's sick.
Oh yes, okay. So this picture is something that you all know every day. Like here, the current that comes out here is like this picture, the electrons flowing in the copper. Something you know about. Now, an electrolyte, is this a word that you've done in chemistry? Yeah, you've done it. Do you know what it is? How would you describe it if you know it? No? Yeah, you see it with the plates, don't you? There's usually two plates. Do you remember what they're called? Yeah, go on. One of them is called... Yeah, that's one of them. Anode and cathode. And the ions are... yeah, and what's the other one? Anions, yeah. We don't go that advanced. An electrolyte is a chemical that conducts electricity. It is actually used in batteries to make ions flow to produce current. You just need the first sentence, okay? Just the first sentence. Oh, and you know what ions are. You don't need to write that down. What are ions? What are ions? Yeah, ions are just atoms with an extra or missing electron. So just write down the first sentence, okay? Chow, just the first sentence. And have you done this picture in chemistry with Lorraine? No. So how did you know about cathodes and anodes if you haven't done this picture?
Yeah.
Oh, right, okay. Okay, fine.
You drawing a picture?
I think I need you to have that picture as an example. Yeah. Okie dokie. Still drawn, that's good. Ah, now we've got sunshine.
So what is the water?
Yeah, we haven't done that yet. That's in a different lesson. It's called a resistor. So in this picture, it could just be like a light bulb or something. Got that? Okay, continuing, Joe? Yeah?
Mm.
Okay. Now, which way should we say the current flows? Is that Kim? Was that Kim? No, okay. Which way should we say the current flows? So if you look at this picture, I turn on the switch and the electricity flows and the light bulb goes on. Okay. This is a battery. This side is called the positive side and this side is called the negative side. So do we say we go from positive to negative, the current, or do we say it goes from negative to positive? So do we say the current goes from positive around negative, or do we say the current goes from negative around positive? Who knows this?
So yellow is negative, right?
In this picture, yellow's positive. Yeah.
Positive is negative.
Positive to negative, go with. Bad news. I'm sorry, really sorry to tell you this, but it's both. So I need to explain exactly why we can say both. So in this picture here, when you have a current, you normally say it goes from positive to negative, like you said. However, the electrons are actually moving from negative to positive. So this is unfortunate. So we say the current is positive to negative, so that's the current, but the electrons actually move from negative to positive. So you have to be very careful in the exam, you know? If they say which way is the current, well, it's positive to negative. If they say which way does the electrons flow, negative to positive. I know it sounds like it should be the same, because we said current is the movement of charge, but it's actually the movement of positive charge, and electrons are negatives. So the normal current is positive to negative, and the electron flow is negative to positive. So just to be clear, okay, just one sec, Siva, just to be clear on this point. If an electron moves from A to B, we say there's a current from B to A. Yes, B to A. Even though the electron moved from A to B, we say there's a current from B to A. Now, the why we'll get to in a moment. So I would like both the picture, these points, and this, okay? Because I can't have you confused on this. It's very confusing. Still cold, Siva? Yeah. Did you have more sleep last night?
Yeah.
You seem more awake today than yesterday. Are you doing any assignment in chemistry at the moment? No essay yet? No? Alright. Have you talked about the labs you'll do next semester? No, I think you do them in January maybe. I'm sure. I think one of them is titration. Which is what you're doing now. Okay. Do you have that, Chad?
Near.
Nearly, okay. Obviously, electricity is a recent part of physics. You know, and it's not quite. I don't think it's as difficult as mechanics. It's not as bad. Okay, got that, Joe?
Mm-hmm.
Yes?
Yep.
Okay. Now, why? Well, you can thank Benjamin Franklin for this. Does anyone know Benjamin Franklin? Yeah? What did he do that's so great? Or what's he famous for, if you know him? Yeah. But I'm talking about in he truly like he is I think on the currency, isn't he? But what thing did he do that in science that he's famous for? Now I think you might know, but you might not know it's him. Does anyone know what he did?
No.
Yeah, no, go on, yeah.
The light.
Yeah, what did he do? I think you might know.
I don't know how to say it.
Yeah, he did the experiment with the lightning, or at least
Oh, the kite and the light.
the kite
Yeah.
and the lightning with the key, you know. Anyways, I doubt that's true because I'd imagine doing that would kill you. But he did do a lot of experiments with charge, you know, positive and negative charge. The problem is the problem that we had the last slide is because we call electrons negative. Now you might be thinking, but electrons are negative. But tell me this. Which hand is this, left or right, for me? Left. This is my left and this is my right. Okay? But there's nothing about this that makes it left and makes it right. It's just our choice. Okay? If all of you switched left and right, so if all of you said, this is now right and this is now left, if everybody did that, there'd be no problem. Because it's just a name. It's a name to tell the difference between one and the other. There's nothing lefty or righty about this. You know? You can do the same thing with charge. If you called electrons positive and protons negative, the reason you call them positive and negative is only to show that they're different. There's nothing positive or negative about it. Do you understand? Unfortunately, it would have been better if we called electrons positive and protons negative. That would have been better. Because it would have meant in this picture here, the electron flow and the current is the same. But because we didn't, or because Benjamin Franklin didn't, it makes the situation we have today. There's a funny cartoon, you can look at it later in the YouTube. But it would have been much better if it was the other way around. Stephen Hawkins talked about this in his book. You know, he said it would be so much better if we all just switched to saying electrons are positive and protons are negative. But you can't, because what happened was people called them positive and negative before they even knew what they were. You know, people were using electricity before they actually knew about the electron or the proton. You know, we only really know about the electron and proton since about, you know, about 120, 130 years. We kind of knew about electricity for maybe like 200 years, you know, so this is the problem. Okay, so now on to some units. So we use the amp to measure current. Now you can actually see that, well, maybe not in that. Does anyone have a plug for their phone? A charger? Somebody has a charger with them? I know, come on, somebody must have a phone charger with them. You have one?
Yeah.
Yeah. Yeah, it's like one that goes in the wall here. No. If you look at the plug, you have it? Look at the front of the plug where the pins are. Turn. No, turn. Yeah. Is there any writing on it, the front of it? Or anywhere on it?
No. Oh wait. There's some writing here.
Yeah, can you see if it says what the current is? It would say something like a number followed by the letter A. Maybe like 1A?
24A.
No, it couldn't be 24 A's. 24 amps?
No, no, 0.5.
Okay, that's better, yes. 24 amps would be a powerful charger.
0.5.
Yeah,
0.5.
0.5.
Yeah, okay. So that will allow half an amp of current. Okay, half an amp of current. I need to give you the definition of amp, and you won't like it. I'm sorry. It's very, very bad definition. It's a very hard definition. 1 amp of a current will produce an attractive force of 2 times 10 to the minus 7 newtons per meter between 2 straight parallel conductors of infinite length and negligible cross-sectional area placed 1 meter apart in a vacuum. So, in other words, if you have 1 amp and 1 amp, you'll get a force here of 2 times 10 to the minus 7 newtons. Because remember, we said you have the law of charges, and current is just a flow of charge. So, yeah, this is a very bad definition. But the good news is they've never ever asked for it in the exam. So that's something. So if you can just give me your pen there. So what we're saying, if you can look up, is if you have 1 amp here and 1 amp here, and the current is flowing, okay, you'll get a force between them. And that force will equal 2 times 10 to the minus 7. And that's what 1 amp is. Okay. Now, I don't think you need to memorize this for the exam, but you do need to add it to your notes with the picture showing 1 amp and 1 amp and the small force between them. And you do need the whole definition. There's nothing to cut out here. Got it all ready, Siva? Yeah, including the picture?
Yeah.
Yep. The picture is important because if you have the picture, at least you have a chance to remember the definition. You know, because in the picture you can see it's an amp, it's 1 meter apart, and you have this force that appears between them. Yeah, it's a really tough definition. The reason the definition is so tough is because it needs to be like this to make the units work. You know, the amp and all the units in electricity. All the other definitions are actually easier because this one is so hard, you know. So we will do other units, and their definitions are much easier. But like I said, it's because this one is so technical and hard, it lets the other ones be easier. Because you can define other units using the amp. So if you have a technical definition of the amp, then you can define the other units easily by relating them to the amp, which has a technical definition. You know. You remember we said at the start in week 1 that you have 7 SI units, 7 basic SI units, and one of the basic units is the amp. The 7 SI units are really important, so they all have very technical definitions. We actually didn't do any of the definitions, you know, like I didn't define what a meter is. You think, well, everybody knows what a meter is. This is a meter. Yeah, well, that's not, you know, that's not good enough in physics. You need a very technical definition of a meter. I didn't tell you what 1 kilogram is, did I? Because you all know what 1 kilogram is. But these all have technical, very technical definitions. And you just have seen that here with the amp, which is one of the SI units. Okay? They all have very technical definitions, you know. Like to define the meter, you need to talk about the speed of light. You know, so they're all very difficult definitions. And like I said, I don't think you'll have this one in the exam, because they've never asked it. It's too difficult. Okay, next now. The Coulomb. So the Coulomb is how you measure charge. I don't know if you've done this unit in chemistry. You have? In physics before, yeah. So the Coulomb, the symbol is C, is the SI unit, the International Systems of Unit for electric charge. So what is a Coulomb? It's the charge you get in 1 amp in 1 second. And you can actually write it as a formula, where Q is the charge, I is the current, and T is the time. So in other words, if you have 1 amp for 1 second, then the charge you get is 1 Coulomb. Okay? So you can see this definition of a Coulomb is actually not so difficult. You can say like 1 Coulomb of charge is equal to 1 amp for 1 second. So if you have 1 amp and it travels out for 1 second, then the charge that you get here will be plus 1 Coulomb. That's what I'm saying here. And you can actually make a formula. Charge equals current multiplied by time. Q equals IT. You probably have seen this formula before in physics. So you definitely need this definition. And we'll talk about how big a Coulomb is. 1 Coulomb is actually a lot of charge. We'll talk about that in a moment. So if you can write this down, please.
All of them?
Yeah. Well, you can skip the first sentence. So you can just say the Coulomb measures charge. And then I need the formula. So, and this sentence. So you can say, the Coulomb measures charge. It is the charge transported by 1 amp for 1 second. The Coulomb measures MEASURES, charge. CHARGE, yeah. And then just start from this sentence. It is
why not use that for both the
For what?
Q?
Ah, but this isn't the definition of Coulomb, this is charge. It's a bit like, what letter do you use for time? T, not S, you know, because S is for seconds. Oh, you're saying why not use C for charge, because charge begins with a C?
Yeah. No, I mean, Coulomb is a unit.
It's a unit, yeah. Yeah. It's a unit that measures charge. Doesn't look like Kim is making it to class. Was she sick yesterday? The weather's not good. Okay, you got this? How big is 1 Coulomb? It's actually pretty big, because one electron has a charge of only minus because it's an electron, 1.6 times 10 to the minus 19 coulombs. So actually a little electron, this is how much charge it has. So you can imagine 1 Coulomb, that's a lot of electrons, it's a lot of charge. Okay. In chemistry, you probably just say the electron's charge is -1 and the proton's charge is +1. Now the reason I'm using the quotes is because there's no unit. You know, if I said the charge is -1 what? Or +1 what? So in physics we use the Coulomb to measure charge. We often actually write this as -E, that's the charge of an electron, and that's actually on your calculator as a constant. Let's see, I'll show you here, Joe. It's 23, constant 23 on the lid.
So do you need to know that, the charge?
No, because it's on the calculator. Do you have this on the calculator?
I have it back home when I go back for the break.
Fine, okay, grand, yeah. Or -1, quote. I'll write the value down, I won't kill you. E equals 1.6 times 10 to the minus 19. Got that? Yeah? Okay, continue? Yeah? Right. Here's a very easy one. We only have one formula for today. Our only formula is charge equals current multiplied time. That's the only formula. So, my question is, 100 milliamps flows in a copper wire for 2 seconds. What is the charge? Okay, well, use this formula to tell me what the charge is. And just be careful, it's milliamps. Okay. So what's the answer?
0.2.
0.2. Are you sure? What's the unit?
Coulomb.
Coulomb. 0.2 coulombs. Yeah, did you get that? 0.2 coulombs. Yeah. And that's all. Congratulations, the first lesson. Not so bad, huh? Yeah. Yes. we'll try the questions for a few minutes and then start the next lesson, okay? You should have no problem. Easy peasy. So if you want to try the questions for a few minutes. Yeah. 0.2 coulombs. Now, because the questions are so easy, question 1, 2, 3, so easy, I have to give you a hard one, which is number 4. Okay, exactly right.